Hello and welcome to ControllersTech. This is the fourth video in the STM32 Modbus TCP server series. In the previous videos of this series, we covered how to configure an STM32 as a Modbus TCP server, and how it handles various function codes when a client wants to read or write coils, inputs, and holding registers. Today, we will continue with the STM32 as a Modbus server. Specifically, we will look at how a client reads input registers. Unlike holding registers, input registers are hardware registers, meaning they are not stored in a database. Instead, their values are read directly from the STM32 hardware. To demonstrate this, I will connect a potentiometer to the STM32 through its ADC interface, and the client will directly read the ADC value through the input register. I will also demonstrate the use of holding registers, where the brightness of an LED will be controlled by the client, by writing a value to the holding register. Now let's look at the function codes we will be using in this video. Function code 3 and function code 6 are used by the client to read and write holding registers. Function code 16, which is 0x10, is also used to write to holding registers, but allows writing to multiple registers at once. Function code 4 is used by the client to read the input registers. I will continue using the Mongoose networking library for this project as well. Before we proceed, let me briefly explain what Mongoose is and why we are using it. Mongoose is an open-source networking library, designed specifically for embedded systems and IoT devices. It is written in C, which makes it very lightweight and a great fit for microcontrollers like the STM32, where memory and processing resources are limited. What makes Mongoose particularly useful is the wide range of network protocols it supports out of the box. This includes HTTP, HTTPS, WebSocket, MQTT, and of course, Modbus TCP. Because Mongoose handles all the low-level networking in the background, you do not need to write complex networking code yourself. You can simply focus on building your application logic. Another thing worth mentioning is that Mongoose is trusted by well-known companies in the industry, such as Siemens, Texas Instruments, Renesas, Samsung, and Bosch. The fact that these companies rely on it in their own products is a strong indicator of how stable and production-ready this library is. For this series, Mongoose is a natural choice. It gives us a clean and straightforward way to implement a Modbus TCP server on the STM32, without having to build everything from scratch. Now that we understand why we are using Mongoose, let's open the Mongoose wizard. Here, we will load the previous project. Browse to the previous project folder, then navigate to the Mongoose folder and open the Mongoose wizard JSON file. Next, go to the Settings section and make sure it is pointing to the same directory we used in the previous project. The goal here is to keep all the server-related code within the same project, so we continue building on top of the project we created in the first video of this series. Now, the holding register container is already in place from the previous video, so we do not need to make any changes to it. What we do need is a new container for the input registers. To do that, copy the existing container, and paste it right next to the holding registers container. Then rename the label at the top to input registers. Before making further changes to the container, let's first open the REST API section. You will notice that the holding registers API endpoint is already there from the previous video. We need to add a new endpoint for input registers. Click to add a new endpoint and name it input registers. Set its type to array, since we want to work with multiple input registers. Also, make sure to mark it as read-only, because as mentioned earlier, input registers are hardware-based, neither the client nor the web UI can write to them, they can only read the values. Now add one attribute to this endpoint named value, set its type to integer, and initialize it with the value 0. With that done, go back to the page content section. We now need to update the input register container so that it uses the new input register's API variable. Click on the text part of the container and change the register address to 30001, since input registers begin at address 30001. Then click on the input field and update it to use the input register's value attribute from the new API variable. That covers all the changes we need to make in the Mongoose wizard. Click Generate Code to generate the updated project. All the changes we made previously in the STM32 project will remain untouched, only the Mongoose project folder will be updated to reflect the new configuration. Now let's import the updated project into Cube IDE. The project has been imported successfully. Let's open the mongoose glue.c file. As you can see, the functions related to input registers have been generated, which confirms that our Mongoose wizard configuration has been correctly applied to the project. Before we start writing any code, let me walk you through how the hardware is connected to the Nucleo H755 board. I have connected a potentiometer to pin PC0, which corresponds to ADC1 channel 10. The potentiometer is powered using the 3.3 volts pin from the STM32 board itself. The 16-bit ADC value from this potentiometer will be directly fed into the input register, which can then be read by the web UI, or any Modbus client. I have also connected an LED to pin PA3. We will use PWM to control the brightness of this LED. We need to use a 16-bit pulse value for the PWM, so the brightness can be directly controlled by writing to the 16-bit holding register. Now let's open STM32 Cube to configure the hardware according to this setup. As mentioned, I will be using pins PC0 and PA3. However, both of these pins were previously configured as GPIO outputs for coils in the earlier project, so we need to disable those GPIO configurations first. Now let's configure pin PC0 as ADC1 channel 10. Go to the ADC1 section and enable channel 10. If the option is available, make sure to select single-ended mode. By default, the ADC is set to 16-bit resolution, which means the output values will range from 0 to 65,535. This range matches exactly what the input register expects, so no additional changes are needed there. I will increase the sample time slightly to slow down the conversion rate, as we do not need the ADC to sample at a very high speed for this use case. You will notice an error in the clock configuration. This is because the ADC clock has been set higher than its allowed limit. To fix this, I will change the ADC clock source to peripheral clock, which uses a comparatively lower clock frequency. You can also reduce the clock by adjusting the PLL multipliers or dividers if needed. With the ADC configured, let's now set up pin PA3. This pin can be configured as timer 2 channel 4, so let's do that. Open the timer 2 settings and enable PWM generation on channel 4. As mentioned earlier, we need the PWM pulse value to range from 0 to 65,535, so set the counter period to the value of 65,535. This means the PWM duty cycle will be directly determined by the value from the holding register. A value of 0 gives a 0% duty cycle, and a value of 65,535 gives a 100% duty cycle. If you would like to understand more about how PWM works, and how the prescaler and counter period affect the PWM frequency and duty cycle, I have covered this in detail in a separate video, which you can find in the top right corner of the screen. That covers all the changes we need to make in CubeMX. Go ahead and generate the code. Alright, the project has been generated, so let's head back to Cube IDE. As you can see, the functions from the previous video are already present here. We will keep the holding register functions as they are, since we are using them in this video as well. Now let's create a new section for the input registers. The input registers will follow a similar structure to the holding registers, so the initial definitions will look familiar. I will define a database array for the input registers as well. Now, I did mention earlier that input registers are hardware registers, and do not strictly need a database. However, since I only have one potentiometer connected to the STM32, I can only feed a real hardware value into one register. To demonstrate the remaining registers, I am using the database for those. In total, I will define 6 registers. The first one will hold the live ADC value from the potentiometer, while the remaining 5 will use the database values. Now let's rename the read function to read input register. It will still take the register number as a parameter, and by default it will return the value from the database. I will remove the write function entirely, since input registers are read-only, neither the client nor the web UI can write to them. Next, we need to bring in the ADC logic. Since the first register is meant to hold the live ADC reading, inside the read function we will add an address check. If the address of the first register is being requested, we will call a function called readADC to fetch the current ADC value and return it. For any other register address, the value will simply be returned from the database. Now let's define the readADC function. This function will return a 16-bit unsigned integer. Inside it, we will call the ADC read sequence to read the ADC data in polling mode, and once the value has been read, we will return it. Since the ADC is already using 16-bit resolution, we do not need to modify the raw value, we can simply return it. Next, we need to write the getter function for the web UI. To do that, copy the input register array and the getter function from the glue file, and paste them into the main file, where we will modify them. First, we need to define 6 elements inside this array, since we want to display 6 registers on the web UI. Also rename the array to my input registers to avoid a naming conflict, as the original name is already defined in the glue file. This getter function will be called by the web UI whenever it wants to fetch the current values of the input registers. This function will first calculate the array size and perform a size check to make sure the request is valid. If everything looks fine, it copies the data from the register array to the web UI. Before copying the data to the web UI, we need to make sure the register array holds the latest values. To do this, we fetch the latest data by calling the read input register function, and pass the requested register number as the argument. The fetched data will be stored in the input registers array, which can then be sent to the web UI. The rest of the logic, including fetching the live ADC value for the first register, and returning database values for the rest, will all be handled inside this read input register function itself. This approach is consistent with how we implemented the holding register getter function. Now for the final step, updating the Modbus handler. We defined this handler in the previous video, but now we need to extend it to support input registers as well. Inside the Modbus handler function, you can see the existing conditions that handle the holding register function codes. We will add one more condition to handle function code 4, which is the function code used by the client to read input registers. When this function code is received, we will call the read input register function, and pass the requested register address to it. Everything else will be handled internally by that function. Just like we defined the read ADC function for the input registers, we now need to handle the LED brightness control on the holding register side. We will do this inside the write holding register function. The LED brightness value will be used from the first holding register. So inside this function, we will add a check. If the write request is targeting the first register, we will update timer 2's capture compare register 4, which is the register that controls the PWM duty cycle for the pin the LED is connected to. We will pass the holding register value directly to this register. Since both the holding register and the capture compare register accept values in the range of 0 to 65,535, no conversion or scaling is needed. I will also initialize the first holding register with a value of 0, so that the LED starts in the off state by default. That covers all the changes needed in the Modbus logic. Now let's move to the main function. Before initializing the Mongoose library, we need to start the PWM output. To do this, call the HAL PWM start function, and pass timer 2 and channel 4 as the arguments. This will start the PWM signal on the pin the LED is connected to. After the Mongoose initialization, we need to register the custom handlers. The Modbus handler is already registered from the previous video, so no changes are needed there. The getter and setter functions for the holding registers are also already in place. What we need to add now are the corresponding handler registrations for the input registers. When registering the input register handler, make sure the API variable name you pass matches exactly what was defined in the REST API section of the Mongoose wizard. For the second parameter, pass the getter function, which is my get input registers. Since input registers are read-only, there is no setter function, so pass null in its place. Next, just like we defined a WebSocket reporter for the holding registers, we need to define one for the input registers as well. The web UI uses WebSocket reporters to periodically fetch and display the latest register values, so this step is necessary for the input register values to appear on the web UI. Now let's build the project. You will notice 22 build errors. These are not caused by anything wrong in the code we wrote. If you look at the error details, you will see that they are all related to HAL ADC initialization and start functions. After some investigation, the issue turns out to be that QIDE does not always automatically include the ADC source files in the driver build path. This is a known but minor issue and is easy to fix manually. To fix it, open the project folder, navigate to the drivers section, then open the STM32 HAL driver source files folder. You will find the ADC source files already present there. Copy those files and paste them into the HAL drivers source folder inside your project. Now build the project again. This time there are no errors. Alright, then let's flash the project to the board and open the serial console so we can monitor the logs. As you can see in the serial console, the Modbus server has started successfully. Mongoose has been initialized and the board has been assigned an IP address. I am using a static IP in this case, but even if you are using DHCP, you should still see a valid IP address appear at this point. Let's open that IP address in a browser. Here we have the web UI showing all 12 holding registers and 6 input registers. Notice that the first input register is continuously changing. This is because the ADC is actively reading the potentiometer and the value fluctuates slightly. Now I will turn the potentiometer and as you can see, the value of the first input register changes accordingly. The potentiometer is at the maximum limit right now, and the value has also reached its maximum of 65,535. As I turn it back, the value decreases as well. The ADC is responding correctly and we got the full 16-bit values ranging up to 65,535. Now let's test the LED. The first holding register is currently set to 0, so the LED is off. I will increase this value and as you can see, the LED turns on at a very low brightness. As we continue increasing the value, the brightness increases as well. This confirms that both the ADC and the LED are working correctly through the web UI. Now let's test the Modbus client. I am using the Simply Modbus TCP client software for this. I have connected it to the server's IP address and port. First we will perform a read operation for 6 registers starting from address 30,001, which is the address of the first input register. The software automatically sets the function code to 4, which is the correct function code for reading input registers. Let's send the request. We have received data for all 6 registers from the server. You may notice that the first value appears as a negative number. That is because the data type is currently set to 16-bit signed integer in the software. Let's change it to 16-bit unsigned integer. Now it displays a value of around 34,000, which matches what is being shown on the web UI. The other 5 registers are also displaying the correct values that we set in the input register database. Now let's take a closer look at the raw request and response to understand what is being exchanged between the client and the server. The request sent by the client is structured as follows. The first 2 bytes are the transaction identifier, which is 00, followed by 01. This is a unique ID that the client generates for each transaction, and since this is the first one, the ID is 1. The next 2 bytes are 0, which is the fixed protocol identifier for Modbus. After that, the next 2 bytes are the length field, which tells the server that 6 bytes will follow after this length field. These 6 bytes of length include 1 byte for the unit identifier, which is 0A, this is the slave ID we set in the Modbus client. Then comes 1 byte for the function code, which is 04 for reading input registers. The next 2 bytes are the starting address, which is 0 since we are reading from the very first register. And the last 2 bytes represent the number of registers being requested, which is 6. Now let's look at the response from the server. The first 2 bytes are the transaction ID, which matches what the client sent. The next 2 bytes are again 0, the fixed Modbus identifier. Then comes the length field, 00, followed by 0F indicates that 15 bytes will follow. These 15 bytes include 1 byte for the unit ID, 1 byte for the function code, 1 byte indicating how many data bytes are being sent, which is 0C or 12 in decimal. The remaining 12 bytes are the actual register data. Since each register is 16 bits wide, each one occupies 2 bytes, and 6 registers therefore produce 12 bytes in total. Now let's test writing to the holding registers. Click on the Write tab and a write window will open. I will write to one register at address 40001. The software automatically selects function code 6, which is used for writing a single holding register. Let's write the value 0, and as you can see, the LED turns off and the first holding register on the web UI also updates to 0. Now let's write a different value. I will write 20,000 and you can see the LED turns on at a moderate brightness. As we write higher values, the brightness keeps increasing. Writing the maximum value of 65,535 brings the LED to full brightness. So the client is successfully able to read input registers and write holding registers on the STM32 server. The LED brightness responds in real time to the values written by the client, and the input register values accurately reflect the hardware state of the potentiometer. This confirms that the full communication between the Modbus client and the STM32 server is working as expected. We can also read a single register instead of a range. For example, requesting just address 30,001 returns the current ADC value of the potentiometer at that particular moment. This concludes the STM32 as a Modbus server part of this series. We started this series by setting up the STM32 as a Modbus TCP server using the Mongoose networking library. We then looked at how the server handles function codes for reading and writing coils and discrete inputs. After that, we moved on to holding registers, where we saw how the client can read and write data stored on the server. And in this video, we added support for input registers, where the register value is read directly from hardware, in this case, a potentiometer connected through the ADC. We also tied the holding register to a real hardware output by using it to control the brightness of an LED through PWM. In the next video, we will shift to the other side of the Modbus communication. Instead of the STM32 acting as a server that responds to requests, we will configure it as a Modbus client. This means the STM32 itself will be the one sending requests to read and write data from another server. It is a very useful configuration in real industrial setups where multiple devices need to exchange data with each other. That is all for this video. I hope the explanation was clear and easy to follow. You can download the full project from the article linked in the description below. If you have any questions or run into any issues, feel free to leave a comment, and I will do my best to help. Keep watching, and have a great day.